Section 5.4 on binomial distributions. We're starting with an example. Kevin Durant is a professional basketball player, and currently, I just looked this up at NBA stats, he makes 90% of his free throws. I am jealous. Suppose that he tried 10 of them. How many do you think he would make? Well, of course, 90% of 10 would tell us that he's going to make 9. So when it says expect, that means the mean, and you just multiply n times p, or find 90% of 10. So we would expect that he's going to make 9. Well, since we have the mean, it would also be nice if we had the standard deviation. The formula for the standard deviation is pretty quick and simple. The standard deviation is the square root of the n times the p times the q. And so that turns out to be 0.949. These two little formulas are not in the calculator. You will need to use them yourself. They are on the formula card, so they're not very hard to memorize. You could just memorize them, but they are also on the formula card that you can use on exams. So another example, true-false test. So that means there's a 50-50 chance if you guess. Suppose that you have 20 questions, and let's see, to get a B, you would need 16. So if you just guess, would it be unusual to get a B? So here's the setup. P is 50% chance, Q is 50% chance. There's 20 questions, and we're going to try to get 16 correct. So we set up the mean, n times P. So this is saying on average, if you guess, you're going to get 10 of them right, 50%. The standard deviation is going to be 2.236, and now we just do the z-score with z equal to the score 16 minus the mean divided by the standard deviation. And then that turns out to be bigger than a 2, so yes, that would be very unusual. Is that normal? Well, what I mean by that is when you do that rule about the z-score being over 2 or under -2, that applies to normal distributions or bell-shaped graphs. Is that what we have here? So take a look. I'm going to take away the x equals 16 and just say, look at all possibilities. If n equals 20 questions, you could get 0 right, 1, all the way up to all 20. So what does the distribution look like? Is it a bell-shaped curve? Well, first of all, here's the probability distribution table. So if you notice at the top, x equals 0, the chances of getting 0 right is very, very, very small. So that would be a very small bar. Then this is a little bit bigger, until you get to the middle, which is right here where the mean is. That would be the biggest, 0.7176 would be the tallest bar. And then notice that it's symmetric, and it would go down again. Or if you just put that into Excel, here's what it looks like. That definitely looks like a bell-shaped curve. So in general, for binomial situations, there is a bell-shaped curve or normal distribution if n times p is bigger than 5 and n times q is bigger than 5. In a way, what that's saying is if your sample size is big enough, it's going to surpass, both of these will surpass 5, and you will have a bell-shaped curve. So then for another example. In the game of blackjack or 21, there's a 44% chance of winning. Suppose a person won 23 out of 30 games. Is this unusual? Or in other words, should the dealer or the pit boss suspect the person of cheating? Well, first of all, here's the setup. The chances of winning 44%. That means the chances of losing 56%. The person's going to play 30 games, and x equals 23 is how many they won. So first, let's check that rule about n times p and n times q. Both of those are definitely bigger than 5. That means we can use the z-score. It's valid. And then we need the mean and standard deviation. So the mean is n times p, which I'm not going to do again because I just did that right here. The n times p is the mean. And then I need the standard deviation, which turns out to be this 2.719. And finally, the z-score. So you just take the score of 23 minus the mean of 13, which that part right there is saying the person won an extra 10 games. And then is that unusual? Well, this definitely goes past the 2.0, so yep, that's very unusual.